Hello everyone, I'm Wei from the Center for Optics, Photonics and Lasers, University of Laval. Thanks to the committee for the invitation. Today I will talk about multiplexing of optical vortices in silicon photonics circuits. First, I would like to acknowledge the co-authors, including our very bright students Yuxuan, Zhongjin, Simon, and my colleague and collaborator, Professor Leslie Rush. The capacity of the transmission systems can be simply described by this equation. The log term represents the spectral efficiency that is determined by the SNR. The factor 2 represents the use of two orthogonal states of polarization. The total capacity is then given by the spectral efficiency times the spectral bandwidth of the entire system and the number of spatial paths m. The figure shows the evolution of transmission capacity in fiber optics over the last 20 years. The left axis is the rate and the right axis is the channel count. The bottom two lines show the symbol rate and optical interface capacity. The state-of-the-art systems can now deliver 800 gigabits per second per wavelength. And this year at OFC, our group demonstrated the first single carrier terabits per second transmission using an all-silicon modulator. Through coherent detection and advanced modulation format, the state-of-the-art WDM systems are now approaching quickly to the Shannon limit. Due to the log dependence on SNR, very marginal gain can be actually achieved by further improving the SNR. So the space is regarded as the only remaining dimension for continuous scaling of transmission capacity, which has been deployed by existing submarine systems with tens of single-mode fibers used as so-called space division multiplexing or SDM 1.1. For next generations, multi-core and multi-mode fibers have been actively examined. As we can see by the curve on the very top, a huge number of WDM times SDM channels, more than 10,000 in total, have been demonstrated in recent lab experiment. There are two types of modes that has been actively investigated. The first is linear polarized mode. LP modes were explored as the first solution for mode division multiplexing. However, due to the strong model interaction, complex MIMO signal processing is usually required. The other group of modes use the orbital angular momentum of light. Optical transmission through OEM modes has recently attracted a lot of attention due to its potential for less complexity in digital signal processing and thus lower power consumption of the system. An optical beam that carries an orbital angular momentum has a null in the center, and that is usually called optical vertex. It has a helix-shaped wavefront and is characterized by an integer number called topological charge, either positive or negative, which is written as L here. The wavefront is composed of L times distinct but intertwined helices, with the step length of each helix surface equal to L times wavelength. The helix can be either left or right-handed, depending on the sign of the topological charge. OM fibers are usually designed with a ring-shaped waveguide core. Here is an example of a ring core fiber produced by the group of Professor Younes Masadek at the University of Laval, which supports more than 30 OEM modes. Generation and multiplexing of OEM modes into optical fiber is, however, non-trivial. They are typically created using devices such as space light modulators or cuplates in a bulky free space setup, which is very expensive and vulnerable to vibrations and other perturbations. Because power splitters and combiners are used for multiplexing, the insertion loss increases with the number of modes. So it is in general not scalable for a large mode count. In addition, the polarization needs to be carefully manipulated since the fiber OM modes are circular polarized. So similar to WDM systems, integrated solutions are demanding for real applications of OEM in an optical transmission system. Over the last few years, we have seen some very interesting demonstrations of OEM generators on silicon chips. The essential ideas of all this device is to impose a phase distribution determined by the topological charge for twisted wavefront. For example, University of Bristol developed a microring-based OEM emitter using periodic scattering elements in the ring cavity. It's very compact with a radius of only a few micrometers. However, it's wavelength selective. So as the topological charge depends on the resonance. Therefore, it is not compatible with WDM systems. Another example shown here is from UCSD. It uses a circular surface grating with a thermally controlled phased array. Alternatively, one can use nanophotonic antennas like this example from MIT. Despite the very cool demonstrations, this device emits cylindrical polarization, either radial or azimuthal. That is not compatible with OEM fibers that require circular polarization. So towards a WDM-compatible polarization diverged solution for fiber transmission, we proposed an OEM generator and a multiplexer consisting of a phased array and 2D optical antennas that can achieve one-to-one mapping from a number of single-mode inputs to distinct OEM modes. Using the transfer matrix method, this procedure of mode conversion can be described by this equation. M on-chip is the transfer matrix for the on-chip linear optics functions, and Q indicates the order of single modes input. Assuming we want to generate n times OEM topological charges times 2 orthogonal polarizations, we should have 2 times n inputs in total. All the modes are emit from the same aperture of the antenna array, so it essentially functions as both an OEM generator and a multiplexer. So the number of the 2D antenna determines the maximal OEM modes. For example, 17 antenna accepts 34 inputs, so it can generate and multiplex 34 modes in maximal. The 2D optical antenna takes 2 inputs, both in TE and TE modes of the silicon waveguide, but with a phase difference of either positive or negative 90 degree, so that a left or right circular polarization can be generated. The 90 degree phase shift is introduced using directional couplers, which can be treated as an integrated version of quarter wave plate. So in this case, a broadband 3 dB splitting ratio is very important to maintain the correct polarization. The phase distribution at the wavefront is introduced by a pair of star couplers, one for left and the other for right circular polarization. All these linear optical functions are described by transfer matrices. The total matrix M on chip is then a product of all these functional blocks. Ideally, it should be an identity matrix for one-to-one mode mapping, but in practice, there are 9 diagonal elements that represent the crosstalk. We can see that our structure provides a scalable solution in the sense that the mode count can scale as the number of emitters. To investigate the performance of this device, we developed numerical models for all the components and then performed the analysis of entire circuit using the transfer matrix method. The optical antenna and the star couplers are simulated in FTTD. The optical antenna is designed for vertical emission. Here's the simulated results. And we can see that the beam is very well confined within an angle of 10 degree. Then we let the beam propagate in free space and interfere with the Gaussian beam as a reference to observe the vortex pattern. This figure shows the results for 5 emitters that can generate 5 OM modes with topological charge ranging from -2 to +2. On the top is the near field intensity. We can see 5 bright spots as expected. In the middle is the phase distribution, and the bottom, the interferograms, which show clearly the vortex pattern. So those are numerical results are very encouraging. So we moved forward to experiment. We made a design based on the standard 220 nanometers thick silicon wafer. The device uses 17 2D nano antennas connected to a 34 waveguide phased array, as shown in this SEM image. The entire emitter is about 80 micrometers in diameter, still very compact. The 2D grading region has a uniform pitch of 600 nanometers in both axes, with a whole radius about 100 nanometer. 4 periods of Bragg gratings are added after the square 2D grading region to improve the vertical emitting efficiency. With this design, the 2D grading antenna achieves about 40% up-emitting efficiency. The device was fabricated using an e-beam process at Applied Nanotools. Metal heaters are applied on top of each waveguide in the phased array to compensate for phase errors due to fabrication imperfection and wafer non-uniformity. This figure on the right shows our experimental setup. It's configured in a very flexible way so that we can characterize our device in either transmitter multiplexer mode or in the receiver demultiplexer mode. To characterize the crosstalk, we tested our device in the demultiplexer mode. A polarization controller is used to convert the output of a tunable laser to either LP, left circular or right circular polarization. We monitor the power on all demultiplexed outputs through a single mode fiber array. Here are the experimental results for crosstalk mirrored with zero-order OAM input. For example, for an input in left circular polarization, all the power should ideally go to the port that corresponds to zero-order OAM in left-only circular polarization. Power found in other fiber ports is crosstalk to other OAM modes, which are shown in solid red on this figure. If we don't do any phase correction, the worst crosstalk for both polarizations is about 0 dB, which means that more power were detected in the higher order OAM channel than the actual target zero order OAM channel. Clearly, the phase errors during fabrication are severe and has caused degradation of constructive interference in the target channel. So on the figure, the holly bars represent the measured crosstalk after applying phase error correction by optimizing the heater voltages. We managed to significantly improve the crosstalk by up to 22 dB. So the worst case crosstalk was measured to be around -6 dB for left circular polarization and around -12 dB for right circular polarization. We then observed the interference patterns in the transmitter multiplexer modes from OAM -3 to +3. We can clearly see the impact of polarization in this case. The first row shows the results when the generated vertices and the reference Gaussian beam are both in left circular polarization. We can see the spiral patterns very clearly, but in row number 2, the polarization of the reference beam is switched to right circular polarization. As a result, only Gaussian-like background is observed. Similarly, in row number 3, the polarization states of the vertices and reference beams are swapped, but still opposite to each other. We still don't see anything interesting in this case, but eventually in row 4, when both of them are in right circular polarization, spiral interference are showing up again. So these results confirm the generation of OAM in circular polarization from our device. So the last row here is just our simulation results for the purpose of comparison. To demonstrate the WDM compatibility of our design, we repeated the interference experiments at swept wavelength. The spiral patterns becomes less clear when the wavelength deviates from 1550 nanometers. The maximal and minimal wavelengths included in the Fourier represent the extremes we were able to cover. When we go beyond these extremes, the spirals in the third order OAMs becomes corrupted. The extreme wavelengths for left and right circular polarization are offset by around 5 nanometers. The overlapping region from 1540 to 15 nanometers represents the exploitable range of our chip, which is about 17 nanometers. The worst case crosstalk of our current design is still very high, so the bandwidth cannot cover the entire bandwidth. Those can be improved by the future optimization of the components. In particular, we believe the imperfection of the performance is due to the non-optimal directional coupler design. So as shown in the figure on the left hand is the splitting ratio respectively measured using the two inputs of the directional coupler. There's about 2 dB deviation from our design due to the fabrication errors, and also we can see a strong wavelength dependence that can be improved, for example, using a broadband MMI. To explore the scalability of the solution, we swept the performance for different antenna numbers and calculated the worst case crosstalk. In this case, we have used a new design of a broadband directional coupler. For each antenna number, we did 1,000 times simulations with a random phase noise. The blue curve here shows the case when we are able to control the phase error around or below 6 degrees of each waveguide in the phased array. We can see that the crosstalk is well below minus 30 dB for a number of antennas ranging from 5 to near 40. Remind that the antenna number equals the maximal achievable mode count. Therefore, these results indicate that the overall multiplexing capacity can be scaled up without sacrificing performance. And if we manage to decrease the phase errors to around 2 degrees, as shown by the red curve, the crosstalk can be further reduced to below minus 40 dB. These results are very encouraging, but might be a little bit optimistic since our impairments, such as other impairments, such as misalignment, is not considered in our simulation, which will be investigated in the future work. In summary, we have proposed and demonstrated an on-chip multiplexers of optical vortices in circular polarization. We can generate 7 OAM modes in both circular polarizations over a 17 nanometer optical spectral range within the C-band, providing 14 OAM channels in free space and 12 OAM channels in an OAM fiber. So this provides a scalable solution for future SDM systems. For example, assuming an interface rate of terabits per lambda, terabits per second per lambda, a petabits per second link can be realized using, for example, 100 WDM times 12 OAM channels. So last, I would like to acknowledge Huawei Canada and NSERC who sponsored this project, and thank you very much for your attention.